In Lesson 4.7, you'll learn how to determine whether two matrices are inverses and find the inverse of a 2x2 matrix. How are inverse matrices used in cryptography? With the rise of internet shopping, ensuring the privacy of a user's personal information has become an important priority. Companies protect their computers by using codes. Cryptography is a method of preparing coded messages that can only be deciphered by using the key to the message. The following technique is a simplified version of how cryptography works. First, assign a number to each letter of the alphabet. Convert your message into a matrix and multiply it by the coding matrix. The message is now unreadable to anyone who does not have the key to the code. To decode the message, the recipient of the coded message would multiply the opposite or inverse of the coding matrix. Now, they said this was a simplified version. I'm sure actual computer programmers have much more challenging techniques to apply. Recall that in real numbers, two numbers are inverses if their product is the identity 1. Similarly, for matrices, the identity matrix is a square matrix that, when multiplied by another matrix, equals the same matrix. If A is any n by m matrix and I is the n by n identity matrix, then A times I equals A and I times A equals A. So the identity matrix for 2x2s is a 2x2 matrix. It has 1s going in a diagonal from left to right. The identity matrix for a 3x3 is a 3x3 that has 1s going in a diagonal from left to right as well, and 0s everywhere else. The identity matrix for multiplication I is a square matrix with 1 for every element in the main diagonal from the upper left to the lower right and 0 in all other positions. For any square matrix A of the same dimensions as I, A times I equals I times A equals A. Two m by n matrices are inverses of each other if their product is the identity matrix. If matrix A has an inverse symbolized by a to the negative 1, then A times a to the negative 1 equals a to the negative 1 times A, which is the identity matrix. Determine whether X and Y are inverses. So again, when we multiply, we're going row by column. So 3 times 1 is 3, plus negative 2 times 1 is negative 2. And first row, second column. So 2 times 3 is 6, plus negative 2 times 3 is negative 6. Starting over, second row, first column, negative 1 times 1 is negative 1, and 1 times 1 is 1. Negative 1 times 2 is negative 2, and 1 times 3 is 3. So I get 1, 0, 0, 1. Okay, that's a good beginning. Since multiplication of matrices is not commutative, we've got to check the products in both orders. So now we're going to start over, and we're going row by column. So we've got 1 times 3 is 3, plus 2 times negative 1 is negative 2. First row, second column, 1 times negative 2 is negative 2, 2 times 1 is 2, looking good. Starting over, we've got second row back to the first column, so 1 times 3 is 3, 3 times negative 1 is negative 3, and 1 times negative 2 is negative 2, 3 times 1 is 3. When we simplify that, we also get 1, 0, 0, 1. So finally, I get to conclude that yes, they are inverses. Okay, when I take row times column here, 3 times 1 is 3, plus negative 1 times 2 is negative 2. 3 times negative 3 is negative 9. Plus negative 1 times 4 is negative 4. Okay, we're kind of done for. I'm going to finish multiplying it because it feels funny not to, but that cinches it right there. Okay, 4 times 1 is 4, negative 2 times 2 is negative 4, and 4 times negative 3 is negative 12, Negative 2 times 4 is negative 8. So this one we won't have to worry about verifying by going both directions, because if the first one doesn't work, we're done for. The inverse of matrix A is given by 1 over AD minus BC. Okay, we've seen that somewhere before. AD minus BC, that's the determinant. And then they switch the order here of the diagonals, so the A and D switch places, where the B and C just switch signs, where the determinant cannot be 0, because we know division by 0 is undefined. To find the inverse, we're going to have 1 over the determinant, and you want to do that first because if the determinant's 0, you're all done anyway. So the determinant's going to be 2 minus 0 times, okay, the signs going, the two places going south are having a good time, and so they do-si-do. And those of us left in the north are cold, so we just change signs. There's my north-south illustration again. So 2 minus 0 is, of course, 2. And by lucky happenstance, those are all even, well, mostly even numbers. I guess 1 isn't, but it's not too bad. So we get negative 1, 0, negative 4, negative 1/2. I can live with that. That is the inverse of the one we started with. So again, we start off with 1 over the determinant. So negative 4 times 3 is negative 12, minus negative 12. Houston, we have a problem. It can't be done. There is no inverse here. An identity matrix is a square matrix with 1s on the diagonal and 0s in the other positions. Two matrices are inverses of each other if their product is the identity matrix. The inverse of matrix A is 1 over the determinant times, and then the guys going south, do-si-do, the guys going north, change signs where the determinant cannot be 0.